Extreme Laboratory Physics.
In today's lab, we're going to investigate conservation of momentum during an explosion. Now, one of the difficulties about measuring conservation of momentum is that we need to measure the velocities of the carts, and to do that without using sophisticated equipment is it's tricky. So we're going to use a clever technique today and measure the conservation of momentum during an explosion. Okay, so we're going to have a before and after situation, as we always do in conservation of momentum. And imagine if we took a cart like this. Here we have cart A. On it we have a plunger, and cart B is right here, like that. And what we've done is we've tied a rope or a string or something like that between A and B. And then we make these carts explode. The two carts push on each other, and they're going to fly apart until the string stops them. So here's cart A and cart B. And the fronts of the carts maybe started like that. They started, here was where the front of each cart was. And this one goes a displacement B, and this one goes a displacement A. If momentum is conserved, then P initial, or P before, equals P after. But of course here, if the carts are sitting at rest and then they explode, they fly apart, the momentum before is zero. So the momentum afterwards has to be zero. Let's take a look at the details of that zero momentum. We have the mass of cart A times the velocity of cart A afterwards, plus the mass of cart B times the velocity of cart B afterwards. Now, one thing that we've done that's interesting by tying these two together is that we've eliminated the need to actually measure time or velocity in this case. We know velocity, of course, is velocity of A is the displacement of A divided by the amount of time that A took to make that displacement.
And the velocity of B is also the displacement of B divided by the amount of time it took for B to move that displacement.
So let's actually replace that in here. Let's say that 0 equals mass of A times the velocity of A, which is the displacement of A, divided by delta T A, plus the mass of B, displacement of B, divided by delta T B. But something interesting occurs when these carts fly apart. Because the one string stops them, it stops them at the same time. They stop at the same time. As soon as that string is taut on A, it's also taut on B, and it stops those carts. So, something that's interesting, delta TA equals delta TB. Let's just call that delta T. So I have 0 equals mass of A, displacement of A, divided by delta T, plus mass of B, displacement of B, all over delta T. Well, those of you mathematically inclined will see that something interesting can happen to delta T. Since delta T is in both of these, we can multiply both sides by delta T, and what happens? Delta T goes away, because we multiply delta T goes away, and delta T times 0 is 0, so we get 0 equals mass of A displacement of A plus mass of B displacement of B. Well, let's just rearrange this a little bit. And we would get mass of A displacement of A equals mass of B displacement of B. But of course, one of these has to be negative. Oh, why don't we make this one negative? And rearranging, we could set this up as two ratios, and we could say that the mass of A divided by the mass of B equals the negative displacement of B all over the displacement of A. Mass of A divided by mass of B equals negative displacement of B divided by the displacement of A. This is true if momentum is conserved. So in this experiment, what we're going to do is we're going to test this out with a bunch of different carts of different masses. And if the mass of A divided by the mass of B equals the negative displacement of B divided by the displacement of A, then it looks like momentum is conserved. Now I'm going to show you experimentally how you're going to pull this off. We have our two carts here. You're going to get the mass of the cart. It's actually written on the cart. And this one's 806 grams. This one's 794 grams. You won't be able to mass these on our scales because they're too massive. So you're going to put the two carts together. Take some masking tape. Put it on the table. I'm going to need a pencil. So I've put a mark where the front of each cart is because we need to know how far the cart's traveled. All right, we have our strings attached to both of the carts. Better get all the stuff out of the way. All right, out of the way. And then I'm going to take my thwacker and I'm going to thwack the cart. All right, now you needed good eyes. You needed some good eye people to see where the two carts stopped, or at least where one of them stopped, okay? You may have to do it several times until you see where the cart stopped. If you see where one of them stopped, you'll put it back in that position. Take the other cart and spread it out, put it in that position, and now you're going to need to measure the displacements of the cart, right? This cart went from here to here, and from here to here. You're going to have to measure the displacement of each cart to see that momentum is conserved. All right. Now what you're going to do is you're going to try another experiment where you're going to change the mass of one of the carts. You're going to take the plunger, push it down, and then up on the lip like that. So let's take a look from the side. So you push down and then up on the lip like that, and it catches like that. And what this little knobby thing does is it just pushes the whole doinker like that, and it goes up like that. Line my carts up again. And then I'm going to put a mass on one cart. You're generally going to want to do it on the cart that doesn't have the trigger because that way you'll have room to get your thwacker in there. If you put it on this cart, now it's in the way of your thwacker, and you can't thwack properly. You must thwack properly when you have an explosion. Okay, I think we're all right. So now I'm going to thwack this. You'll also notice when I put the mass on there, I put it in front. You don't want it back here because when it goes out like that, you don't want it sliding. So whenever I put my masses on, I put them right on the front so they don't slide. So now I'm going to thwack, and hopefully you had someone seeing where one of them ended. And if you didn't, you have to redo it. You have to keep doing it till you see where it ended. You put up, you measure the displacements, and then you see if the equation seems valid. Good luck to all of you.